Welcome to Excel 2013 Statistical Analysis video number 34. Hey, if you want to download this workbook, and this is the Chapter 5 second file, click on the link below the video. Hey, in this video, we want to talk about the Poisson experiment or a Poisson discrete probability distribution, and ultimately about the amazing Poisson.DIST function. But what we're going to do here is we're going to remind ourselves actually of this discrete probability distribution that we already created. Now, a couple of videos ago, we collected some data on number of arrivals at Dick's Hamburgers at 45th Avenue in Seattle on Saturday noon lunch hour. And we counted during a 1-minute period the number of people that arrived. We had this entire list, and we defined X as arrivals during 1 minute. There were some minutes that 0 people arrived. There were some minutes when 1 person arrived, all the way down to the bottom, control down arrow, to one time when 14 people arrived in 1 minute. Then we built a frequency distribution. Here was our X, random discrete variable from 0 to 14. We did frequency count ifs. We got our count, we got our total, and we calculate relative frequency. This was our probability distribution, and from this we could calculate probabilities. But what if you didn't have this data set, or you didn't have this probability distribution that you created? Well, if this data set meets a requirement of a Poisson experiment, then we can use the Poisson function to actually create a distribution just like this. And we will do that over here in just a moment. But we need to check whether the properties or requirements for a Poisson experiment are met. Now, the probability of an occurrence or success is the same for all equal-sized intervals. Now, remember, for binomial, we were talking about successes over number of trials. Now we're talking about successes over a period of time, 1 minute. Now, the first one just means that we can use these probabilities over any 1 minute period. Second, the number of occurrences or successes. That means number of people arriving that occurred in any interval is independent of the number of occurrences or successes in any other interval. And that sort of makes sense for our Dick's Hamburger restaurant example, because the number of people arriving in 1 minute are not going to affect the number of people arriving in the next minute. The other requirements, the probability of an occurrence or success is proportional to the size of the interval. That just means if the interval doubles to 2 minutes, we would double the mean or double the proportion. And that's true. The mean and variance have to be equal or near equal. And when we did this example earlier, we calculated these, but we didn't really say anything. And in fact, they are almost equal. So that is another characteristic of the Poisson distribution or a Poisson experiment. And as always, with all of these distributions, if the actual relative frequency pattern from our past data fits whatever distribution we're using, in this case a Poisson pattern, then we can use our function. Now, I've already plotted this, and this is from our raw data, our original data. In a moment, when we plot from our Poisson function, we'll see that they're pretty much exactly the same. So all those characteristics are met here. So you're not going to believe this. Again, this means we don't have to have any of the original raw data. We don't have to have created this. And the only thing we need is the mean over this 1 minute period. And we have it. It's 3.88. So check this out. I'm going to do equals Poisson.DIST. It only wants the X. These are the number of people arriving during our 1 minute interval. And the only input we're going to need is the mean. So as long as you know the mean, right? You working at Dick's, you know that the mean from past data is 3.88. You can go ahead and use this function, comma, and the cumulative or probability mass, that's exactly the same. When you want the exact probability for a discrete probability distribution, you use that 0. Close parentheses, Control Enter, and I'm going to copy it down. Now, notice one thing, and we'll talk about more detail about the Poisson distribution on this next sheet. But this is one of those situations where we have people arriving. And even though the mean is 3.8, So the tallest column better be right about here. And you can see the biggest probability is right about there. But because this is a line situation, right, we could have 0, 1, 2, 3. It could theoretically go to any big number you want. It's just when you calculate the probability, it's like 0.0000000, and there's some little teeny number out there. Hey, we better add all these up at the bottom. Alt equals, and it better equal 1. Remember, all probability distributions, each probability has to be greater than or equal to 0, and the total has to be 1. Now, let's just compare this. Look at this. They are not exactly the same, but they're pretty darn close. And you got to remember that when we use Poisson and other distributions, it is the estimate that we're using. It's a model we're using for the original data set. But you can see straight across that these are unbelievably close. So we had a 1 input of our mean. We can go ahead and calculate this. Now let's plot this. And I'm going to highlight all the way down to the bottom. Insert, column, column. And just like with our binomial, it's picking up the random variable 0 as one of the column heights, and it needs to be down here in the horizontal axis. So I'm going to click on the columns, delete. And there it is. Now I'm going to delete the legend, click on the title, type in equal sign, and I'm going to scroll up. I have a title up here in N1. You can see the formula and enter. I'm going to change the font size home, change it up here to 10 and enter. Come to the plus. We definitely want our axis titles. Let's see if I can, yeah, right on our vertical equal sign, and then click on P of x relative frequency. That's not the right title. I'm going to hit enter. This should be P of x Poisson function. Down here, I'm going to click equal sign. That throws me up to the formula bar, and x is arrivals during 1 minute. Now let's compare and contrast these. If I drag this down here, actually we can put these right on top. The only difference is we extended this one way out. This one isn't, but you can see it's basically got exactly the same probability. Look at that. Here's the 0.2, the 0.5. So it's looking amazingly similar. So that means in this example here, we're just proving to ourselves that if we had the source data, we plotted it over here, did all the steps, that things are going to look pretty darn similar. Now that means we can just later use our Poisson, and we will on the next sheet. Now let's calculate our mean. Remember, the mean and variance are supposed to be the same. So we're going to calculate some product for our expected value. We take our x values. We did not have to extend it this far. I just did to show you that that could be done. And here's our probabilities. Remember, some products got to be exactly the same. For a second there, I was not. And enter. So look at that. There it is, 3.8796. So right over here, looking like pretty darn exactly the same. The variance, some product, and we take our x values. So I have the x values minus the mean, close parentheses, caret 2. Comma, and I need my probabilities. Control Shift down. Now you can let go of the control and just hold Shift and up arrow. Close parentheses. I'm going to control backspace to jump back up there. There's our formula and enter. So when we do it from our Poisson function, they're exactly the same. Now I want to go over to this sheet and talk a little bit more about Poisson distribution and look at some other examples. So Poisson discrete probability distribution, used to estimate the number of occurrences or successes over a specified interval of time or space. And you want to think about this. Whereas binomial counts the number of successes over a specified number of trials, Poisson counts the number of occurrences or successes over a specified interval of time or space. Good for estimating the probability of line weighting situations where you know the mean number of arrivals over a certain time interval, or distance of road or pipe intervals or any other type of physical intervals where you know the mean number of repairs or whatever over a certain distance of that interval. So for example, from past data, we know the mean number of water line breaks is 25 per 100 miles of pipe in Richmond, California. With this information, we can make estimates about the probability of a certain number of water line breaks over a 100-mile stretch. Now get this. Again, Poisson only requires that we have the mean over some interval. For this distance, it's 25 line breaks over 100 miles. For this Dick's Hamburger restaurant example, it was 3.88 people arriving per 1 minute. So the interval was minute here. Down here, it was 100 miles. But in both cases, we knew the mean. Here's our properties. We talked about those. And here's our P of x, the probability of x occurrences in an interval, height of the column when you plot it on the chart. Discrete random variable is x number of occurrences over a specified interval of time or space. And there's no upper limit, right? We know that in a line, usually the upper limit, from our sample data for Dick's restaurant, it was 14, right? But theoretically, you could have some whatever upper limit. So that's the set of x's we get. And as x increases past the mean, the probability decreases and gets quite small. That's a misspell there. Now, usually you're just given the mean, but that's always going to be calculated from past data. Our formula right here, which you can do this if you want to have a couple examples of doing the formula, but we're going to use the Poisson.DIST. We take the mu, raise it to the x times that magic number e. Now, e is approximated by 2.71828. In Excel, you can get it by going equals exponent of 1. And that'll give you e. You would take e and you raise it to the minus mu and divide it by x. Really excited. No, x factorial. So in Excel, we'll use Poisson.DIST, x mean, and cumulative. All right, let's scroll down, and we have 3 examples. Now, our first example is the same example we've been using. Dick's Hamburger restaurant, Saturday lunch rush. We know that there's 3.88 people arriving per minute. Now, we want to calculate exactly 0. So I'm going to come down here, equals PO and tab. That'll give us our Poisson.DIST function. We need our x, comma, and the remarkable thing about this function is all we need besides the number we're trying to estimate is just that mean, and it'll calculate the rest. Comma, 0 gives us our probability mass function. That's the height of the column or the probability. Close parentheses and enter. Now, if you wanted to do it longhand, that beautiful formula right here, there is mu, or expected value, raised to the x times, and that's how we get our e, exponent 1, raised to the minus mu, or expected value, divided by factorial x. We don't want to do it that way, though. Now, I do want to do the whole table and show you a little trick here. Now, I've already put a 0 to start this off, created the Poisson.DIST function. And now remember, in our original data set, we only had 14. So we could do that. But the Poisson function is going to assume that this can go on a lot further than this. So check this out. Here's how I figure out how many cells to drag down. Alt equals and enter. So it's pretty darn close to 14. And for our original sample data set, it got that far. But now I'm going to actually delete that sum and copy it down. And just bring it down to, say, something like 30, and then come down to the bottom, Alt equals, and enter. So when I start to get a 1, or however far I want, then I stop. Now, I have plotted this already. Here is the plot. And we want to do a couple more examples here. Now, we had x equal to 0, but now we want to calculate the probability that we can have in 1 minute 3 to 5 people arrive. What is the probability of that? Now, we saw this between criteria back in the binomial video, our last video with our counting students withdrawing from class example. And here we're going between 3 and 5. If we're going to do this between, we got to talk about the cumulative function. Remember, if we give the function a 5 and a 1 as the last argument, with our binom and with now our Poisson.DIST, it'll always go from the low end up to whatever x we give it. So if we're trying to go between 3 and 5 inclusive, well, we're going to put a 5 in to get the probability from 0 to 5. That'll be all of the probability. Then we need to subtract not 3, because we need to include 3, but we need to subtract 2. All right, so you ready? Equals Poisson.DIST. We're going to start with our 5, comma, and our mean, comma, 1 for cumulative. That always goes from the low end to whatever x we put in. That's the probability from 0 up to 5. F2. Now we need to subtract Poisson again. And this time we're going to put a 3 in because that's what we got. But we really need 2, so subtract 1. Comma, and we get our mean, comma, and 1 for cumulative. Now, this little bit right here will get 0, 1, and 2. All of that probability will be added and then subtracted from all the probability up to 5. And enter. And there's our probability. So the probability of 3 to 5 people arriving in 1 minute is 55%. Now, our next example, we want to calculate the probability that 2 people will arrive in a half a minute. Yeah, a half a minute. We were given number of people arriving within 1 minute, but it's no problem. We can, how many half a minutes are there in 1 minute? 2. So we take our mean and divide it by 2. We have to do that before we can calculate this. Now we have a new mean divided by 2, so equals PO. Our x is going to be 2 people arriving in a half minute, comma, our mean for a half minute, comma, and 0, close parentheses. So the probability that 2 people arrive in a half a minute is about 27%. All right, now let's look at our next example here. From past data, we know the mean number of arrivals for an accounting tutor is 3 per hour during the morning shift. Now, if we assume that the probability of a person arriving is the same for all equal size intervals, and the number of people arriving in any interval is independent of the number of people in any other interval, we can use the Poisson.DIST function. Now, our goal is to calculate the probability that 5 people will arrive in 1 hour. People isn't with an R. Gotta get rid of that. Enter. All right, so we come down here. Our random discrete variable will be x, number of arrivals in 1 hour, equals Poisson.DIST. Hey, there's our 5. That's the number of people arriving within 1 hour, comma. We have our mean, comma, and this is exact, so I put a 0 for that probability mass function. Enter. So the probability is about 10% that 5 people will come in over the hour. There's that long, ridiculous formula. Now let's look at our third example for Poisson distribution. From past data, we know that the mean number of water line breaks is 25 per 100 miles of pipe in Richmond, California. So our goal is to calculate the probability that 30 or more breaks will occur over a 100-mile stretch. Actually, we'll do a few different calculations here. Let's first come down here and calculate all of them. So I actually made this one big and tall here. Equals Poisson, P-O-S tab. Our particular x is going to be 0, comma. We got to go and get our mean. The mean water breaks per 100 miles, F4 to lock it, comma, 0, close parentheses. That 0 will calculate exactly the probability, and I'm going to copy it down. And then Alt equals to add them up and enter. So oh, there's our chart. Look at that. All right, so what's the probability of 30 or more? Now this is greater than or equal to, so we got to go over to the 30 bar, and it's somewhere right about there, and we want everything from there up. So this way, anytime you're doing the upper end, we're going to take 1 minus, because the function goes from the smallest all the way to the x. Now the 30, we actually need that on the upper end. So when we plop this 30 into our Poisson.DIST, we're actually going to have to subtract 1. But remember, we're going to take 1, which is everything, and subtract from the smallest one all the way up to 29. So here we go. Equals 1 minus Poisson. And the x is 30 minus 1. That's the 29. It's going to go from here all the way to 29, comma, and the mean, comma, 1 for cumulative. It'll get all of that, subtract it from 1, and boom, there's our probability. So there's like an 18% chance that there'll be 30 or more water breaks over a 100-mile stretch in Richmond. Now we could also Alt equals, and scroll down here, 30 or more. I'm not going to include the 1. Shift Enter to put that in the cell and jump up. And so either way you slice it, there we go. Now again, so for this discrete probability distribution, we're going to be able to add these up. In later chapters, we're going to have to use these functions. And so the logic we're learning of how they go from the smallest up to some point and subtracting between 2 and minus 1 when you're doing something on the upper end will follow us through the rest of our class. Now, what about less than 10? Well, again, we're going to have to put, wow, 10 is really small. Wow, better be. So anyway, we're going to put in cumulative up to 10, and I want less than 10. So I'm going to have to do minus 1, because I really want to go from the smallest all the way up to the one right before 10. So you ready? Equals PO. X is going to be 10 minus 1. That gives me 9. Everything below 10, comma, and I get my mean, comma, 1 for cumulative, and Enter. Alt equals, and I'm going to add up all the way to 9. And Enter. And so there you go. Well, so here's the deal. That's incredibly small. So if we actually found a 10-mile stretch that only had 10, because the probability is so small, we're like, what are they doing right there? Or what is going on there to cause such an abnormally low number of water breaks? Now, actually, down here on this chart, if you're looking at this, I hope you, when you saw this earlier, you're like, that's not right. Hey, there's a 1 there. It's a 0, because there could be 0 breaks. That means the default is in this chart. So don't forget, when you're making the chart, you got to go up to Design, Select Data, and make sure to edit the horizontal category. Edit. And I'm going to highlight from 0, Control-Shift down arrow. Notice it got the total, so I'm going to Shift up arrow. So that even works in our dialog boxes. And click OK. Click OK. And there we go. All right, so we talked about the Poisson distribution, the Poisson probability distribution. We talked about the Poisson.DIST function. We saw a great example for water leaks over a 100-mile pipe. We saw an accounting tutor example where people coming for tutoring are arriving over an hour period. We saw our Dick's Hamburger example of arrivals. In our next video, last video for this chapter, Chapter 5, we'll talk about the hypergeometric distribution. All right, see you next video.